The next section expands on the idea of the fundamental theorem of algebra. Keep in mind the fundamental theorem of algebra tells you, based on the degree of the polynomial, you know exactly how many complex solutions it has. Complex solutions are the same thing as complex zeros. And recall that if you have a complex solution, it could also be real, it could be a pure imaginary. So we're going to look at these and we're going to factor them over the set of complex numbers, which means if it's a 6th degree polynomial, you should have 6 linear factors. If it's a 5th degree polynomial, you should have 5 linear factors, some of which may be real, some of which may be complex. But I say that, but reals are part of the complex. So we're going to factor these over the entire complex number system. They introduced a new word in here. They're called irreducible over reals. It's a quadratic expression which is irreducible over the reals. Typically we're going to see things like this. It's an x squared plus 16. We can't factor this. These irreducible over the reals means if you had to try to factor that, you couldn't factor. We can factor the difference of two squares, but we can't factor the sum of two squares. And they don't have to be perfect squares either. It's going to be things, anything in the form of a even power plus another integer. So that's kind of what we're looking for the irreducible factors over the reals. They're going to ask us to factor these completely into linear functions and also to state the zeros of the function. So how are we going to approach such a big task? Well, we're going to use technology to help us out. First of all, we're going to look at 7a. And in 7a, they're asked us to write the function as a product of linear and irreducible quadratic factors, and then a product of just linear factors, then a list of all of its factors. So there's three things that we're asked to finish up in this problem. And the first thing I would do is to take your graphing calculator and I would try to find your possible real zeros. Now the real zeros are the ones where you can see where it's crossing the x-axis. I have no problem with you taking your calculator, plugging this into your y sub 1, just put in your y sub 1, your function f of x, then going and using your second calculate function on your calculator, second calculate as zero the function, and then you're going to use those zeros to put into your synthetic substitution or synthetic division, whichever one you want to think of it as. I guess division is probably a better way of thinking of it. To reduce this 4th degree polynomial into lower and lower, they call them depressed equations, into 1 degree lower each time. So here's what I'm advocating that you do. Put this function into your calculator. Use your calculator to find these real zeros. Now these real zeros, in the terms of what we're doing, they're probably going to have to be pretty decent numbers, rational numbers. So we could use our rational zero theorem, but that's a little more time consuming. Find those, use synthetic division to reduce it down to a quadratic equation, and then from there you can either factor or you can solve your quadratic. So let's model what we're talking about here. From the graph, I'm going to look at this graph and I'm going to predict that I bet that a positive 5 is a zero of the function, and because it's a zero of the function, I can then use the synthetic division, put the 5 in your bar, and then I got a 1, 1, negative 26, a positive 4, and a negative 120. If I get a remainder of 0, then I know that 5 is a zero of the function. So then I'm going to draw the line here. The other day I showed you this abbreviated form. I'm just going to drop down the 1. 5 times 1 is 5. 5 plus 1 is 6. 5 times 6 is 30. 30 plus a negative 26 is 4. 5 times 4 is 20. 20 plus 4 is 24. 5 times 24, that's 20, carry the 2. That is 120. We get a remainder of 0. So our remainder is 0. So now I've just depressed this equation from a 4th degree polynomial in this line, and now it's become a 3rd degree polynomial in this line. So I've just assured that 5 is a 0, and its related factor then is x minus 5, because eventually we want a product of linear factors. It's linear because it has a power of 1. So now I'm going to look for another linear function, or another linear factor. I'm going to use this depressed equation, and this time I'm going to go over here on my graph, and I'm going to estimate from that, or I can use the second calculate as 0, and I think that 6, or negative 6, is a factor, or is a 0, and then x plus 6 will become the 0. So let's do this. We're going to drop down the 1. Negative 6 times 1 is a negative 6. Negative 6 plus 6 is 0. Negative 6 times 0 is 0. Added on to 4 is still 4. Negative 6 times 4 is a negative 24. Negative 24 onto 24 is 0. Okay, so I just figured out that negative 6 is a 0, but it was a third degree, so now I've got it down to a second degree polynomial or quadratic. There's no reason to go any further. We've already found our two real zeros. Here's our two real zeros. These other ones have to come from the solution of x squared. There's no x's plus 4. So that's my other factor. Now that's our irreducible factor. It's a quadratic factor, but it won't reduce or factor any further. So here's one of the things they want us to write. If 5 is a 0, then x minus 5 is our related factor. If negative 6 is a 0, then x plus 6 is our related factor. And then here's our irreducible factor, x squared plus 4. If it's an even power with plus, I know it's not going to factor because that's going to give us these complex solutions. So this is one of the forms that they want us to write our answer in as a irreducible quadratic factor, product of linear and irreducibles. Now the second thing we're supposed to do is write as a product of linear factors. Now these two are linear, powers of 1, but this one is a quadratic factor, so we have to factor further. So what I will do is I will take these and I'll go x squared plus 4, set it equal to 0. I'm going to figure out what is the input that's going to create an output of 0, or I'm going to find out the values of x. So that means x squared is equal to negative 4. That means x has to equal plus or minus the square root of a negative 4, which means we have plus or minus 2i. Remember, conjugate factors always come in pairs, should expect that. So when we write our related factors, since these are the zeros, then what do the related factors look like? So the x minus 5, x plus 6 remain unchanged. All we're doing is we're going to rewrite this as a product of linear factors. So if it's a plus 2i, then the related zero is x minus 2i. If it's minus 2i, then the related factor is x plus 2i. And now I have it as a product of linear factors. So that's what that one is. Finally, they want us to write all of the zeros. So we're going to make a list of all of its zeros. Well, if we have the factorization, then the zeros is simply the opposite of our factors. So zeros of the function are 5, negative 6, and then a plus and a minus 2i. You can go ahead and write them as a compound statement like that. But there are, in this case, 1, 2, 3, 4 zeros. It was a fourth degree polynomial. Because it's a fourth degree polynomial, we know it must have 4 complex solutions and 4 complex factors. And a real number is part of that complex number system. The real number is part of that complex system, and a pure imaginary is part of it. So we have accomplished all 3 things that they were wanting us to do in that particular problem. Okay, so let's start over with the fifth degree polynomial. Again, I would put this in your calculator. I would get a picture of this. Sometimes that becomes one of the more difficult things, but to get a picture, I do second calculate. I'm going to guess and infer from this image that we have a negative 3 as a 0, a positive 1 as a 0, and a positive 4. So we'll have 3 pure real answers, but then we'll have 2 other answers. By the fundamental theorem of algebra, there must be 5 solutions, 5 complex solutions. There are 3 just real, but these real are part of the complex. So these are 3 of the complex solutions. The other ones are going to be pure imaginary or more of what we think of a complex number as. So we're going to grab our coefficients out of our polynomial. We've got a 1, a negative 2, a negative 2, a negative 6, a negative 99, and 108. Oops, 108. We want to divide it by what we think is one of our factors. Now I think that I like this 1, so I think a positive 1 is one of our solutions. You can start with any one of these 3. I just like the 1 because it creates smaller numbers right away. So draw my line, just kind of organize a few things here. Bring down the 1. 1 times 1 is 1. 1 and negative 2 is a negative 1. 1 times negative 1 is a negative 1. Negative 1 and a negative 2 is a negative 3. 1 times a negative 3 is a negative 3. Add it on to 6 is a negative 9. Negative 1 times negative 99 is a negative 9. Oops. and I want to add a negative 9 onto 99. So I'm going to make sure I do that. That's 18, carry the 1, that's 108, negative 108, because it was a negative 9. So then 1 times a negative 108 is negative 108, added on to 108, 0. So I've just confirmed that what I'm seeing in my image of my graph, 1 is a 0. So we went from a 5th degree polynomial, now I've got it depressed to a 4th degree polynomial. Now I'm going to use this depressed equation and run synthetic division through it. But this time I'm going to choose, well, it's either the 4 or the negative 3, so I'm going to do the 4. So I'm going to test to make sure that 4 is a 0 this function. So I'm going to draw a new line. I'm going to drop down the 1. 4 times 1 is 4. 4 and a negative 1 is 3. 4 times 3 is 12. 12 and a negative 3 is 9. 4 times 9 is 36. 36 minus 9 is a 27. 4 times 27 is 28. Carry the 2. That's 8 plus 2 is 10. Good. We have a positive 108. Positive 108 plus 108 is a remainder of 0. So now we just depressed it down to a 3rd degree polynomial. We have to keep using our synthetic division because we've got to get it down to a 2nd degree polynomial. So we'll take our last value out here that we suspect from our graph, a negative 3, and now we're going to divide by a negative 3. Draw the line we're looking for and hopefully getting the remainder of 0 just like we had in the others. So bring down your 1. Negative 3 times 1 is a negative 3 plus 3 is 0. Negative 3 times 0 is 0 plus 9 is 9. Negative 3 times 9 is negative 27. Negative 27 minus 0 is 0. So now we're down to a 2nd degree polynomial. I'm finished with the synthetic division, and now I can figure out what this is as a 2nd degree polynomial. So we were supposed to write it as a product of linear factors. So we've got x minus 1. We've got x plus 4. Correct that. X minus 4. And then we have x plus 3 times, and this one is going to be that irreducible quadratic. So irreducible form, that's going to be x squared plus 9. So here's one of the forms they asked us to put our answer in. Then they want us to write them all as linear factors. So here's where I take that irreducible form and I plug it in. X squared plus 9 equals 0, which means x squared has to equal a negative 9, which means x has to equal a plus or minus 3i. So my other factors here are x minus 1 times x minus 4 times x plus 3 times, and it's going to be x minus 3i and x plus 3i. Now those are all the linear factors. Finally, they asked to write down all of the zeros, so there should be 5 complex zeros. So our related zeros are 1, 4, negative 3, and plus or minus 3i. If you count these, there are 5 of them, just like the fundamental theorem of algebra says. You should have 5 complex zeros.